So really appreciate the last speaker and the organizer put that one first because it gave a lot of great introduction to the relevance of that wavelength range and in general look at different wavelength range for understanding the surface compositions of the moon and to keep those wavelength ranges in mind when thinking about instrumentation for endurance or other observations. So instead of looking at mafic minerals, I am looking at volatiles and therefore looking at the polar regions in the PSRs and shadow regions. I'm looking at really comparative planetology, trying to understand or take what we understand of the Galilean satellites and so forth, which are cold like PSRs and implying what we can infer or may need to measure in PSRs on the surface of the moon, which basically are cold traps or even witness plates, as Paul Lucy likes to say, of volatiles throughout the solar system. So without further ado, let's move on to the next slide. Again, we're looking at adsorption, which is different than the crystalline water or any kind of the solid state form itself. The minerals themselves, as people have shown before, such as the Savada, they have significant vapor pressures at numbers that you can see there for the ice phases shown in page et al, with water basically not being stable for geologic times at about 100 degrees Kelvin, right? Okay, and CO2 is even less stable and so forth, and other things more hypervolatile than that. And that's due to the binding energy between those two molecules. However, when you have individual molecules resting on a substrate, they can interact with the electronic environment, the substrate as shown there in the diagram briefly, especially for polar molecules like water. You can have very strong hydrogen bonding and a lot of electronic interactions which stabilize these materials, even for quadrupole moments in CO2, et cetera. So these materials are stable at a higher temperature. Now, the abundance is very low. By definition, this is no more than a monolayer, right? Usually less than a monolayer. And the strengths of the absorption sites vary over the crystal, over the grain that it's resting on. So it's a pretty complex interaction. People have studied this, like Poston and Orlando, looking at the activation energy for desorption. However, although it's complex, it is still a mechanism for increasing the strengths or increasing the temperature at which these volatiles would desorb and leave the system. And it varies with the composition of the volatile, varies with the composition of the substrate and the makeup of it. But in general, these are significant effects of tens of degrees. And to some extent, we can infer qualitatively how much this effect is by looking at other bodies in our solar system, specifically the satellites of Jupiter and Saturn, where we do see these volatiles, and we know they're not ices by their spectral characteristics and basically by the temperature of the surfaces. For water ice, for water, molecular water, we see that at least for the water adsorbed on those bodies, 150 Kelvin, it looks very stable. For CO2, it looks like it's about maybe 100 Kelvin or 110 Kelvin. For other materials, probably much less stable, right? So the point of this talk is to say, okay, these molecules can be stable. What are the spectral characteristics? What can we learn about how to identify them if they're present? And also, what can we learn about the identity of the substrate by looking at the spectral characteristic of the adsorbate, because there's a relationship there. And then these other points I think already hit on. Go back to previous talk about polarization spectroscopy. They mentioned grain size dependency. Yeah, there's more adsorbed water or adsorbed materials on finer grain materials because you have a larger surface area to volume ratio, right? So all straightforward stuff right there. So let's move on to the next slide, since it's already burned up 4 minutes. Next one. Okay, this is basically a review of a very nice paper by Poston et al. He did a couple of papers on this showing, in summary, the blue line is for a northosite. The red line you barely see at all on the left plot or on the right plot. Those are two different ways of looking at the same data. On the left side, it basically said the desorption energy of water from basalt is very low. It's almost like water ice itself. It's rather hydrophobic. Whereas for an orthosite, it's much more stable. This shows, yeah, adsorption actually does happen, okay? And these, although these are lunar samples, they aren't lunar samples anymore because they're brought back to the Earth. the bonds have been passivated, even though these have been heated up and any water has been desorbed, and so they're fresh, they're still passivated. So these are probably even less adsorptive than what you'll find on the moon, where you probably have much stronger bands as well. But the point is, you can potentially have up to hundreds of ppm of adsorbed materials on these, and this is evidence right here that certainly can happen for water and therefore potentially for other volatiles. So it's a relevant mechanism, really for understanding the science of this, not really so much for ISRU. Get to that maybe later. Next slide, please. So yeah, I use infrared spectroscopy like a lot of other folks here do too, to understand the composition, the nature of interaction of volatiles with, stabilizing materials. And this is actually someone else's work, which is quite good, looking at transmission spectrum, in this case, absorption shown as absorption here, within section of a meteorite with water in it. And it's labeled here. You can see the 6 micron band, also, which is evidence of H2O. And so obviously some of that 3 micron region is 2. You have OH. You also have some organics. Next slide. Things are the next step. Organics there, as well as CO2, not shown because telluric band, it's just can't see it, but it would be right there. We see that in the GalSat, and I'm sure JWST has seen it as well. And next slide is what? SO2 should be there on the moon if there's any volcanic activity occur around 4 microns. And I'll get into the details how it would shift between crystalline and adsorbed. And next slide. And if you're only interested in water, you can probably do that multispectrally, tell the difference between molecular water and other phases of water. But as you can see, obviously, if you're interested in all the other volatiles, you really need a hyperspectral instrument. Get to it later, probably about 10 nanometer spectral resolution, right? Next slide. And just some spectra took of a meteorite sample as analog. Doesn't tell you anything more than I just already told you about. So let's move on to the next slide for the sake of time. CO2 on the Galilean satellites and Saturnian satellites is absorbed, has to be at that temperature, and spectrally it is clearly that way as well. The position of the bands vary on these satellites, implying that there's basically the interaction with the material it's absorbed to differs, very likely because the material it's absorbed to is different. Okay, this band is around 4.26 microns in some cases, which is different than water, CO2 ice at 4.27, and different than what we see on meteorites as well. But the point is that it is stable at the colder temperatures, not at the warmer temperatures. You may find this in PSRs. Next slide, please. And for meteorites, it's at these wavelengths, 4.27 microns is at 0. So you can see on meteorites, the absorption band is actually at longer wavelengths, longer than what's seen in water, in the ice, and longer than what's seen on the Galilean satellites. That's because I guess these carbonaceous chondrites are different material than what's on the surface of the Galilean satellites. Very useful capability to say, hey, we know that therefore the adsorbate's different. There's a different material there on those bodies because the adsorbate has a different, or adsorbent has a different spectral characteristic. We can apply this to the moon and potentially infer what the composition of the material is that, if we see this material is on the moon. Next slide. And by doing that, potentially understand its origin evolution. Similarly, sulfur dioxide, which is potential volcanic material. Adsorbate is different than its frost. We haven't done many measurements for this, so I don't have a lot to say on the stability. We looked at CO adsorbed onto clay materials. We can only go down to about 100 Kelvin or so, and CO is truly hypervolatile. It's not stable at those temperatures at all. But but in PSRs, it could be, and it's clear that those wavelengths are far different than the ice itself and are potentially dependent on composition. The ice band is around 4.67, if I remember correctly. All right, so next slide, finishing up, perfect. The 2.5 to 7 micron region is very useful in understanding the presence, identifying the presence of, and the physical state of hypervolatiles that we expect and that we know are on the surface of the moon. And hyperspectral or spectral capability would be quite useful in understanding the potential nature of the adsorbate that these would be stuck onto, because there's a clear relationship between the spectral nature of these adsorbents and what they're stuck onto. Yeah, Yeah, they should be found in the PSRs, even though ICEs may not be. And that is it. So there's 20 seconds left. One quick question if there is one. Thank you.